Have you ever needed a tree with a specific shape and looked for them online and you just can't find a tree that will have the exact shape you need? Now it's possible. You can save hours by easily modeling the shapes you need. For example, filling the corners of a room by just drawing and making anything you can imagine, like a character. The tool is called Anytree, which I have spent months working on, and it's really good at making trees and bushes of any shape. Go check it out on Blender Market to see if it might be useful for you. We will build a light version of it together, which will do some of the stuff the full version does, and also we will learn a lot of useful things along the way, so hang on. First, we need an object to turn into a tree, then we need to make a grid around it, then we need to delete the parts that are outside the object, then we need to merge the remaining things by distance, find the shortest path from one point to all the other ones, then smooth and profile them, add UVs and leaves, and it's ready, and you can use literally any object with the system. So let's get started, and the first chapter is the object. So which kind of an object are we going to use? Not the default cube, but something even better, which is the monkey. We will just open up a new side panel here, open up geometry nodes, press N and start with the next chapter, which is making a grid around the object. So for that, add a new set of geometry nodes, and let's disconnect those so that we don't see the cube anymore. Now what we need is to basically understand how we can make a grid that follows the shape of the object in an extremely convenient way. Our main helper will be the bounding box node. So let's add a bounding box node here, and let's drag in the Suzanne to this node tree. And let's connect the Suzanne to the bounding box and the bounding box to the output. And you see, well, this creates a thing around the Suzanne. For example, when I move the Suzanne around, nothing happens. Well, we have to select the bounding box and change the Suzanne to be relative. And now when you move this, you see the bounding box changes its size and shape, depending on how big or large the Suzanne is. So now we will use this information, this min and max here, to build our own grid system. So first let's pin the geometry nodes tree here so that it doesn't move when I select anything else. And let's add a grid node here. And let's output this like that. As you see, it is currently very small. Let's make it a bit larger like that. This will be our first plate, and this will be moved at the most bottom location of this monkey, and the last one would be at the highest location, right? So let's add some separate XYZ nodes so that we can get some information out of here. So first we have to move this thing at the bottommost location of this monkey, and for that we can use the minimum Z position of this bounding box. So let's add a transform node after the grid like that, and let's drag and let's use this Z position here. So for that, we need also combine XYZ because we cannot put this float Z into this vector translation. Let's put this into the combine XYZ and move this here. So now you see this is exactly at the bottom location, which is extremely good. And when we move the monkey around, it always stays in the correct location. Now we just have to move it around with the monkey as well, because this isn't happening right now. So to move it around, let's look at this from the top. And for example, when I move this on the X like that, for example here, then this should be around here, if I'm not mistaken. And because we are moving the center point of the object, then we are moving this location. We're moving from here to here, this distance between here, and this location just so happens to be the average between the min and the max of the bounds of the monkey. So we need to get the average, right, of the x min and x max. So to make this a little bit easier, I'm actually going to just group those nodes here, and I'm going to calculate the average by using a math node, add those x's together because the formula tells us to do that. This is the formula of the arithmetic average. And I'm going to do this actually for the y as well. So now I can just output those from here and here, press N, group, and call this X average and Y average. Close this, and let's come up from here. Let's call this the ranges. And let's use the X average as the translation and Y average also. So now when we move this monkey around, you see it always is sticking to the monkey, and this is exactly what we need. However, when we make the monkey larger, this size isn't exactly sufficient. It is not changing its size depending on the size of the monkey. So to do this, what we would actually need is to get the size to be the X range, the range on the X axis, and the size Y, the range on the Y axis. So if you want to get the range of something from the negative to the positive, which currently happens to be 2, then we have to subtract from the maximum part the minimum part, because 1 minus minus 1 is 2. So let's build into our ranges system a system for ranges. And let's do this so by subtracting from the maximum the minimum, setting this to subtract, adding here 3 of those. So from the max Y, from the max Z, the minimum Y, and the minimum Z. And now those things here should be output from here. And let's call this X range, Y range, Z range. Let's get out from here, and now we can just use the X range as the size X, Y range as the size Y, and the Z range will be useful in a second. So now this is moving exactly with the monkey, doing everything we wanted to do. And let's just go on and let's duplicate many of those on top of each other so that they act basically as layers along the monkey. So let's use a duplicate elements node, which allows us to duplicate this thing. And currently it's duplicating points, but we don't want this, we want to duplicate faces. And let's add, for example, 10 faces, and you cannot see those because they are all in the exact same location, and we have to move them apart so that we can see what is actually happening here. So let's take the set position node, put this here, and for example, when I put the duplicate index into the offset, you see they slide away like that because the index gets put into all of those at the same time, which means they're going to slide. But we are going to put this only into the Z component. So let's add a combine X, Y, and Z and put this here and put the index into this one. So the first one gets moved by 0, the second one by 1, the third one by 2. To make them move a little bit closer, what we actually need is to alter this index by some ways. And one of those would be to multiply this by a number, for example, by this small one. And now this is pretty much perfect, but we would like this to actually be touching the exact end of this monkey, to be at the last level there, and also taking into account the numbers. So for example, when we add more, they are all stretching together and forming this nice grid for us. And this is pretty easy because when you know the minimum and the maximum position of this monkey like that, let's say this is like the range is 3 between those two, 1.5 and minus 1.5. Then we just have to divide this range by the amount of things we have, which is 29. And we have a small range for each one of those, so they can be placed like that. Let's do this. Let's get the Z range, which we have calculated, and let's use a math node and divide. I'm going to shift right click, drag, reroute here. And let's divide this by this number. So to divide by this, we actually need an integer. And I'm going to take the integer and put this here and add like 11 here. And then we just have to connect this division into this multiplication here. And you see it kind of works. For example, when you add more, it always works, but we're actually having always one plate less. So we can just take a math node and put an addition here and add one plate more. So now we have this grid working perfectly and is ready for our experimentation. So this chapter is finished. If you need to look at the nodes, they are here. And in the next chapter, we will make this grid disappear outside of this monkey, so we only have the inside. So let's convert those into points so that you can actually see what is happening here. So if I convert those into points, well, we kind of have a little, too little right now. So let's just add some more resolution here like that. And I'm going to also turn down the size of those points. So as you see, we have some points inside of the monkey and some points outside. How do we delete those that are outside of the monkey? So if you have a shape like that, for example, we also have some points inside of it, like 2 here and 2 outside. To make the difference between those, what we need is to first find the closest face. Each 3D surface that is polygonal is divided into faces. And for each point, we'll have to find which one is the shortest, closest face to those. Now what we will do is that we will draw a vector from each point to the respective closest face it has. We will do this vector for every point that we have. And at last, we will find the normal of this face that is the closest one. This will be just like pointing to where the face is pointing. You have good normals. If they are bad, you cannot, well, do this. And now we have basically the answer to the question which points are inside, because we can just compare if those arrows are pointing in the same direction. For example, for this, they are. So this is inside, this point and this point is also inside. Because they're pointing in the opposite direction, this point is outside and this point also. So we just have to compare those using a dot product and this will work out. So let's do this. First, we have to find the closest surface element to each point. And for that, we can use a sample nearest surface node that we can put here. And we want to find the nearest surface point of the Susan respective to every point that we have. And we need to know the position of this nearest surface element. So let's take a position and plug this here. So this one is the nearest surface element. Now what we need is to draw a vector from the original point to this nearest surface element. And for that, you can imagine that you have, for example, a grid like that. Want to get from this point to that. This one has the location of 2 and 1. This one has the location of 0 and 0. So the vector by which you have to move is 2, 1, which we get by subtracting from the end the start. If you would do this the inverted way, we would get 0 minus 2 would be minus 2, minus 2 minus 1. This will give us the wrong vector, which we don't want. Let's subtract from the end the start. So from the sample position, the start, and we can use this vector math for that. Subtract from the end position, we subtract the start position, and we get the direction to closest. Now what we need to find is the normal at this same exact surface element. And for that, we can just basically duplicate this thing here and find from the Susan monkey the normal. So let's add a normal node here and plug this here. Now that we know the normal and the direction to closest, we can just use a dot product node. A dot product will output -1 for the arrows that are pointing in the opposite directions and 1 for those that are pointing in the same direction. So now if you preview this with Ctrl-Shift-Click and using the set position as the geometry to preview this on, you can see a problem. You can just set the monkey to the relative position, and if you hide this monkey now, you can see that we have some white things inside which are inside the monkey. So now we just have to make a Boolean value out of those to use this in delete geometry. So if you use delete geometry here and we plug this there right now, we should get a better result. You see the inside is kind of lost, but we actually need the inverse of this. So let's use a compare node and set it to less than 0. And now we have the inside of this monkey. If you see some artifacts outside of this monkey, you just have to add more subdivisions to the Susan by pressing Ctrl-1, for example, and the problems should be solved right now. Now chapter 3 is finished and we can go on to chapter 4. Which is merging them by distance. This chapter only lasts for a few seconds as we take a merge by distance node, well, merge them together, and this is done. So we can move on with the chapter 5, which is finding the shortest path and making this look like a tree. This is how the nodes look before we move on to the chapter 5 about finding the shortest path. So let's move on to chapter 5 and start by adding this shortest path gang here. So we need the shortest edge paths node and also edge paths to curves, and these two are working together to create a tree. Now if you want to know more about those nodes in a very detailed way, there is a Patreon tutorial I have where I literally talk about every input and output these nodes have, different examples, how to find not only the shortest but the easiest path. If you're interested, this is something you could look at. Currently we are just using them at a really low level, so we only need to know that the end vertex is actually the start of the tree, and the next vertex index goes into the next vertex index, and that's all we need. So as a very easy example, this would work something like that. So you can select an index and it starts to grow from there. But the problem is, well, it doesn't look too much like a tree, and it's very hard to find, for example, the lowest index by just changing the number like that. It seems this one worked though. So we will build a system that uses an empty sphere like that. And then it will find the closest point to this empty and use this as the input to this end vertex. So let's do this. Let's drag in the empty here. And I'm going to make some more room for ourselves here. To know if something is closest to an empty, we have to know the distance to every point in this object. So for that, let's use a vector math node and set it to distance mode. And from the location of the empty and between the position of every element we have, I want to find the distance. And this looks something like that. Where the empty is closer, you see it is getting darker, and further away it's getting white, which means it's getting higher as a value. Now we need to find the smallest of those values. So for that, what we can use is an attribute statistic node. I will delete this viewer for a moment, move this thing here. And then we can move this attribute statistic here and find the minimum value, which will look something like that. So that, of course, you have to also connect the attribute here because we want to get the minimum value of this attribute. And you see when I move this thing around, the minimum gets larger, of course. And when I get really close, it gets really dark because it's really close to points. Now we need to find if there is a point that is equal to the minimum distance. And for that, we can use a compare node. I, by the way, pressed Ctrl H to hide this like that. And you can use equal. If the minimum is equal to the distance somewhere, then this is the point that is the closest one to our empty. And as you see, it works very fine, works very nicely. And you see, it just works, So we can use this as our end vertex, like that, and turn on the edge paths to curves with M. And this is something, but it's not definitely a tree. It looks pretty random, to be honest. So when I move this around, it does work. It changes, but it doesn't look very good. And that's because it's not using the edge length as something to consider the pattern by. So we actually should use as the edge cost, which is kind of telling the algorithm which path to travel. We should use the edge length, which we can get by using an edge vertices node. So this gives us information about the one vertex and another one of an edge, and we can calculate the distance between them by using the same distance node, like that. Between the position 1 and position 2, we can calculate the distance, put this to the edge cost, and you will see this looks much better. This looks much more like a tree, I'm going to put this like that. You can see the difference, right? This is before, like that, and this is after. There is definitely a difference. Feel free to look at the notes before we move on to chapter 6 about adding the profile and converting those things into smooth meshes. Let's go on. And to do this, well, there is nothing easier than just using a curve to mesh node. So let's use a curve to mesh, and let's use a profile also, because a good curve to mesh is nothing about a good profile, which looks like that, very thick. Let's use 3 centimeters here, 16 as a resolution to save on performance. Now this looks a bit heavy, and this also is a bit wrong because the branch tips are extremely thick and the branch starts are also very thick. So let's set the resolution, the radius of the curve radius, to the length of the curve, because we need a value that is large here and small here gradually. And the length of the curve, since it starts to be calculated from the branch tips to here, since this one here is our end vertex, the length works very well, and we can just use a spline parameter, put this here, and use the length as the radius. And well, I would say this is pretty good. Looks pretty nice, but it's very, very, very jagged. Let's make this a little bit better. So let's use a fillet curve node and put this, for example, after this thing here, and this looks like a mess, but we are here to solve the problems. Set this to poly and check limit radius, and then tweak the radius manually a little bit like that. And then you can add a little bit of loop cuts or just cuts here. And this looks much better. So this is before, this is after. And you see there are some problems here like that. And these are because we are filleting after setting the curve radius. So the spline parameter is taken like from the wrong curve. So let's just hold down Alt and move this before, and you see the same problem that was there is now solved, which is extremely nice if you have a problem solved. Chapter 6 finished. It's time for a chapter 7, which is adding UVs and leaves. Kind of the last one actually before it is finished and looking like a nice little tree. UVs are no dark magic. They're actually just the direction for the texture. So for example, a UV map like that is just telling us that, you know, you have to move like that on the x-axis and like that on the y-axis. When you combine those as a color vector, this looks like that, very familiar. And this is basically what gives our branches a UV texture. First, what can we use as something that goes along the branch as a UV? Well, something like that is of course the length of the branch, and we can use the same spline parameter as that. Let's preview this spline parameter at, for example, this geometry, and we see absolutely nothing, but we know a solution for that. And the solution is to use a capture attribute. So why do we have to do this? That's because the spline parameter is there for splines. So if I, for example, would look at this at the splines here, you see it's darker up here and brighter down here. And when we convert this to a mesh, there are no splines left, and therefore we don't see this attribute. So we just have to capture the length beforehand and output this now. And you can see now this comes with the mesh and looks pretty nice on its own, even as a texture. I like this. This is our either U or V, doesn't matter. UVA, I would like to call this. And then we need a UVB, which is like the second component of the UV vector. And this is basically just the length of the curved circle here. So let's just use a capture attribute like that. And this moves around. I hate this. So let's turn off auto offset. And let's take this one here like that. And let's put the same spline parameter here. And now we can just preview this at the end geometry. And you see, well, it looks pretty much like something that is going around the branch like that. So let's output those two things as a vector. Let's use a combine x, y, and z. Put this one as an x, this one as a y. Really doesn't matter. You can invert them afterwards if it doesn't work. And let's preview this. This looks like that, like a UV map, I would say. So of course we cannot use this in shaders in any ways right now. So we have to first store this as an attribute, as a named attribute to be more precise. And this is a vector because it's purple. And we can call this a tree UV, which is the exact same name that Anytree uses. If you decide to get this, you should decide to get this. Then we can output this as an attribute like that and delete this viewer here. So now we have this tree UV attribute, and when we go to shaders, then we go to render view and we don't see any difference because we actually haven't applied this material. So let's use a set material at the end of our node tree and select the same material. Now let's, for example, add a checker texture here and preview this. And you're like, well, this looks pretty ugly because we're not using the UVs. So let's use the UVs. And for that, we need to add an attribute node. Attribute. And right in here, you guessed this right, tree UV. Then connect the vector or color to the vector. And look at that, we have those UVs here. They're looking pretty nice, although they're a bit stretched on the length here. So we can just use a vector math, set this to multiply 1 and multiply an axis with a value, like for example 2 in this case. And this looks pretty fine. I'm going to import the materials from this fine-tuned Anytree add-on. And let's use a brown bark, for example. And the brown bark looks pretty good on this little tree here. The next question is, how do we add leaves? And this is exactly what we're going to do now. So you add the leaves, we need some points to add the leaves on. And for that, well, we need some points, as I told you. And I think the smooth curves would look pretty nice as points. So I'm going to take the smooth curves and use a curve to points node like that. And now we have 10 points per each curve. And for small curves, this is very dense. So we don't need this. We have to actually use length. For example, like that. And I think this is working pretty okay-ishly. And let's now instance some things on those curves. So I'm going to use an instance on points. So we need a leaf, and below this leaf we need a stem. And the stem is helping our leaf not to stick into the bark, which looks extremely ugly. So let's use a quadratic Bezier for that, which is a fancy word for a simple curve. Let's use this as the instance. And well, we have some things here, looks rather ugly. I'm going to join this together with the tree in the end so we can actually see what we are doing, right? Like that, so that we don't need this viewer anymore. And actually, let's make some room for us, like that. All right. So currently the quadratic Bezier is just so wrong, so that let's just select everything, put this to 0. And now let's zoom into our tree. And let's start by increasing this thing here. Right, so now you see they are like pointing up from the branches, which is a good improvement. And let's use like 0.05, like 5 centimeters, which is 2 inches for you Americans. Now let's put a leaf on top of each one of those. And we're going to deal with this middle one in just a moment. So here we instance stems. Now we just need another instance on points node, instance on points, and we're going to instance the leaves on those things. So where do we get those leaves from? Of course, import leaves, and we have those here. But of course, you don't have this add-on right now, so I also included those ivy leaves in the description, so you can just get those from there, or you can get Anytree. Put this geometry into instance, and you see absolutely nothing. This is a problem, of course. This is actually a massive problem. Yeah, they are there. You see, right? They're in a wrong position. So we have to do so that we separate those children and also reset them so they are in the correct position. And now when we take the scale down to like 0.1, then you see we have a mess here. So let's select pick instance. So it picks only one leaf per stem, per point to instance on, but it also selects, per every point that the quadratic Bezier has, and it has 16 right now. So we can also turn this down to like 8. But a better way to control this is to use endpoint selection, which is a really good way to just select the endpoints. So put this into the selection, and now it only selects one from the start and the other one from the end. And we need only the end one because the start one is near the branch, and there we don't need this. Also, you probably notice it's pretty complicated to see what we are doing since we don't see those branches anymore, or those stems. So let's turn those stems into a mesh, like that. Let's put a curve to mesh down here, curve to mesh, and let's use a profile curve, as we always do. Let's use a curve circle, put this here, and let's join this together. For example, join geometry, those two things, control, right-click, drag, disconnect, put this here. And you see, right, there are some massive rings here. And we actually need to reduce this thing. So we'll put like 1 centimeter here. Now this is a bit better. So the radius is still a bit massive. So let's use a set curve radius. And we would actually want this to be thicker at the start, thinner at the end. So for that, again, the best node there is spline parameter that we can take, put the length into radius, and you see it is inverted, or actually let's use the factor, and let's use a color ramp to invert this. And this color ramp works in a very nice way, so that we can just invert the handles like that, and this works. And what we also can do is to just use a math node to take down on the thickness a little bit, like 0.1 for example. I don't want this this last end, you don't want this to be like infinitely thin like that. And also goes the same for branches, you don't want this end to be like that. So here where we are using this thin ends, spline parameter, set curve radius like that, let's just use a math node to add something to it, like 0.01, and now this is a bit thicker and looks much better. So let's go up here again, and now we have the radius set to our liking. So now when you look at this tree, you see a huge problem, or actually many of those. But the first problem is that I see is that those stems are very straight, and we want them to be a bit more curved. So for that, you can just go here, curve them a little bit like that. Make sure the Z is at 0.25. Now we see that the leaves are absolutely ignorant at the rotation of the stem below them, so we should actually rotate them or align them to the rotation of the curve. And for that, we can use a curve tangent. that is basically a normal of the curve is like pointing away like that, but a curve tangent is pointing from the curve basically like that. So it's like touching the curve, 90 degrees of an angle from the normal. So we can use the tangent and an align Euler to vector node to align the rotation. Sorry, tangent goes to the vector. To align the rotation to the vector, which is the tangent, using this as the rotation. X, Y, and Z, nothing seems to work. Z actually works. We just have to rotate those leaves a little bit more. I'm going to rotate those on the y-axis actually, like 180 degrees. And now this works pretty perfectly. Things are working nicely. Now a problem that you see probably is that all the leaves are having the exact same size, and we can solve this pretty easily by just using a random value. This is like the bread and butter of geometry nodes. Use a random value like that. And this looks already, I would say, pretty nice. So now they are also rotated a little bit well regularly. They are always pointing up. They should be actually rotated to the branch. So we can actually just drag from the curve to points the rotation to the instance stems, and it doesn't work, it's inverted. So we can just use a rotate Euler. Euler was a guy who has a lot of mathematical accomplishments, and rotation in 3D space is one of those. So we can just rotate the Euler in the local space, and we can rotate this thing like 180 degrees on pretty much any axis. And you see it works all right, but they're all so straight and inside of the branch. We don't like that. So before we send those into this mesh here and instance a leaf, we have this thing. I'm going to add a shift right click drag reroute like that here. I'm going to move those things a little bit here, move those things even more a little bit here. And I'm going to add a rotate instances here that can be used to rotate your instances very easily, like that, for example. And I'm going to add a random value here that is a vector random value, because we have like 3 channels here that we want to randomize. So I'm going to drag this here and drag this one to 0. And now I'm just going to try, and you should do the same thing. Just try and see what you like. I first want them to be like, not so, yeah, I want them to be like that, like a bit pointed upwards along the thing, but not too much. And I also want them to be on the z-axis. They have to be like really randomly rotated around this thing, and maybe also add a little bit of like tilt to them. So I think this looks pretty nice, but we have another problem. The problem is, what is that? That's a huge mess here, and we don't want this. That's because we are adding the leaves uniformly around the whole tree, and this is not very good. So we should actually use a trim curve node and trim the curve before it gets to curve the points. So this looks like that. We are trimming the ends. I think you can see this, right? So we are only adding the leaves to those areas that are, left. And I'm going to delete this, and you see this looks immediately better. So I think around those parameters, this tree looks pretty okay. But the problem is that the stems don't have a material. Well, you can fix this very easily if you just add a material to them. So you can go into the end and use a set material with the meshed stems like that. And we can select the same brown bark that was used. And look at that, the tree is actually ready. Does this work with any object? This is the question of our day. And of course, we're going to try this out with a torus. So let's take a torus, let's make it a little bit smaller. And now let's just go here and switch every object to a torus. And we also have to do this here, torus. And look at that, the system just works, So you can move this thing around, you can select where is this thing gonna work, you can select this torus, go to the wireframe mode, you can move those things, and it's gonna just, work. So this is pretty nice, right? Now this was the tutorial. I hope you enjoyed this, and don't forget to check out Anytree. I would really like to know what you think about that. Have a nice time. See you next time. Time.